So I will discuss matter effects in two flavor oscillations. And I mentioned in the last class that the matter effects arise due to elastic scattering of neutrinos with particles in ordinary matter. So first let us see the various scattering processes. First, let us take mu E. It can scatter of proton or neutron or electron, and we are considering only elastic scattering, which means initial state has to be exactly same as final state. Rather, final state has to be exactly same as initial state. So and if I try to draw a Feynman diagram for it, it would look like there is a mu E coming in and a mu E going out, and there is a proton or neutron or electron coming in and the same particle going out, and they can exchange what is called as Z0. I hope in your particle physics course you have studied electroweak model, so you understand what is meant by Z0. And this gives rise to a potential which we call VNC. NC standing for neutral current. And I put NV there. So this is the neutral current potential which arises for the electron neutrino. And now let us consider nu mu So similar thing, except I replace electron neutrino by muon neutrino, and in the Feynman diagram also and this Feynman diagram leads to a potential which I call VNC nu mu. And okay, here I said in two flavor oscillations, but if I consider three flavor oscillations, there will be mu tau and this leads to now one thing that electroweak theory tells us is that the coupling of, if you look at this Feynman diagram, this vertex is exactly same as this vertex, whereas at this vertex, here there is a nu mu, there is a nu e. But what electroweak theory tells us, and we also call this, we give it a name actually, it's called lepton flavor universality, that the couplings of Z0 to nu e are exactly same as couplings of Z0 to nu mu. So if I am writing an effective interaction potential between nu e and matter and a similar effective interaction potential between nu mu and matter, this effective interaction potential depends purely on the couplings, and so the neutral current coupling for nu e is exactly same as the neutral current coupling, the neutral current potential for nu mu, which is exactly same as the neutral current potential for nu tau. However, there is one important addition we need to consider. That is, I can have a nu e going in and an electron come out, and there will be an exchange of a W, and I can have an electron going in and that becomes a nu e. So in addition to the neutral current scattering processes, this particular scattering nu e e minus to nu e e minus, this particular scattering has a this particular scattering has a charge current contribution, and this Feynman diagram will give rise to VCC nu e. And as we see a little later, that as far as neutrino oscillations between active flavors are concerned, if we limit ourselves to neutrino oscillations between nu e, nu mu and nu tau, I need to worry only about this term. I don't have to worry about the neutral current potential. Whereas right now there is data which doesn't quite fit into the three flavor oscillation framework. It seems to demand that maybe there is a fourth light neutrino. If there is a fourth light neutrino, as we learned from LEP, it has to be sterile. It cannot be an active flavor. It does not have standard couplings to Z0. So if you are considering neutrino oscillations involving such a sterile neutrino, then you need to worry about the neutral current potentials also.
So what defines the iteration for?
Well, in the 1990s, there was an experiment called LSND, which claimed it saw nu mu to nu e oscillation with an L by E, with a L of about 10 or 50 meters, E of 1 MeV. So for an L by E of meter per MeV, they claimed they have seen nu mu to nu e oscillation, but that means the corresponding delta m square is of order 1 electron volt square, which of course doesn't fit in with our solution to solar and atmospheric neutrino oscillation. But there was a lot of fight about whether LSND really saw a signal or not, whether what they are seeing, it can be part of background. And an experiment called, and also another experiment called Carmen, which is more or less a clone of LSND, did not see any such thing. And when I say clone, not an exact clone, but as close to LSND as possible. And they haven't seen any signal. So there is a lot of argument about it. And an experiment called mini boon was constructed, where for LSND, L is 50 meters, E is 50 MeV. Whereas in the mini boon, L is 500 meters and E is 500 MeV, but same L over E. So if there is what LSND saw is really due to is really due to neutrino oscillations, mini boon should have seen a signal. Mini boon has seen something, but you can't be, again, they couldn't make an exact statement that they confirm LSND, or they couldn't make an exact statement they rule out LSND. On the other hand, they have seen something else, which also looks intriguing. And again, there is an argument whether what they see is really signal or are they misinterpreting background. That fight is now there for mini boon also. So the next generation experiment is being designed. Until then, we do have to consider the possibility that there is a fourth neutrino which gives rise to a delta M square of order 1 electron volt square. And if you consider matter effects involving such a fourth neutrino, one has to worry about these neutral current potentials also. And a completely separate thing, there is something also called reactor anti-neutrino anomaly. And people who are enthusiastic about reactor anti-neutrino anomaly, they claim that one can explain it using a sterile neutrino. Yeah, sorry.
Which is the experiment, next generation experiment too?
Yeah, it's being built at Fermilab. I don't know I know the name, but I can't recollect the exact name. It is part of the short baseline neutrino program of, Fermilab has two programs, long baseline neutrino program, Dune is part of that, and this is part of the short baseline neutrino program. Yeah.
Why are we considering neutral current only when they are not a sterile neutrinos and not in?
No. First let me do the algebra, then you will understand.
Does existence of sterile neutrino imply there is fourth lepton?
Whether there is a fourth lepton number, that's a slightly tricky question, because there is no corresponding charge lepton. So right, Le, Lm, Lmu, L tau, they all imply that there is an active neutrino corresponding to a charge lepton. Whereas fourth neutrino, being sterile, it does not require the existence of a charge lepton. So if you want, you can derive such you can propose a lepton number for the fourth neutrino, but off the top of my head, I don't see such a definition being very useful. Now, so let me write down the matrix element for this, and so there is a outgoing electron and an incoming neutrino. So I have G by 2 root 2 E bar gamma alpha 1 minus gamma 5 mu E times 1 over q square minus nw square. The G alpha beta I am neglecting here, times G by 2 root 2 mu E bar gamma alpha 1 minus gamma 5 and for forward elastic scattering, Q is quite, of course, Q here is very small. I neglect it. So actually there is a minus sign here. So this is G squared by 8 nw square. And now I don't know if you have come across this sort of a mathematical operation called Fiat's transformation. There is such a thing. You can look it up in any standard textbook, such as for example Halser and Martin, where if I have f1 bar gamma alpha f2 times f3 bar gamma alpha f4, I can rearrange things so that I can write it as f1 bar dot dot f4 times f3 bar dot dot f2. So basically I put this one here and I put this one here. And the two as far as calculation of scattering matrix elements are concerned, this expression and the Fiat transformed expression, they give exactly the same answer. So if we do that, we get E bar gamma alpha gamma 5 times E times mu E bar gamma alpha times 1 minus gamma 5.
What is a transformation?
Called Fiat's transformation. The proof is quite straightforward. It just takes 2-3 lines. You can look it up in Halsen and Martin. And actually the V minus A has the special property that when you make the Fiat's transformation, product of two V minus A currents turns out to be product of two V minus A currents. If it is pure vector current, then it will not be like this, it will be something else. This is actually a special case for V minus A currents. And now, in the case of forward scattering, the momentum transfer is practically zero. See what is this electron doing? It is sitting more or less at rest in an atom. Okay, it's not exactly at rest, but compared to the neutrino momentum, the momentum of electron is negligible. So it's practically at rest. And after it interacts with the neutrino, in principle it can gain energy, but I'm considering forward elastic scattering, and in such a situation the amount of momentum it gains is again completely negligible. So after the electron interacts with the neutrino, the electron is still sitting at rest. So what we need to do is to consider a non-relativistic wave function both for the initial electron as well as for the final electron. And when I do that, you find that this gamma 5 actually will not contribute, and here only the gamma 0 contributes. When I consider these two to be non-relativistic fermions, we say that the upper larger component and the lower smaller component, and in such a situation the dominant contribution here comes from gamma 0 times 1. Rest of it is negligible. So, and g square by 8 under u square is gf by root 2 times this sort of e bar 0 is, or rather and E bar 0 gamma 0 is E dagger 0, and E dagger 0 E0 is essentially the number density of the electrons. If you look at the quantization, second quantization of a Dirac field, you find that the expectation value of E dagger 0 E0 is the number density of the electrons. So this is gf by root 2 times the number density of the electrons times nu e bar gamma 0 1 minus 1 of 5 . I am missing a factor of 2 somewhere. I am not able to see where it is. But the eventual answer, by the way, one thing you notice, these G's are dimensionless, and these fields, they have mass dimension 3 by 2. So there are 6 fields. So mass dimension, no. Okay. I have to be a little careful. There is a, Now there is a detail I am missing here, but eventually this leads to this charge current potential given by root 2 GF NE. Going from here to here, there are some details I am missing, and unfortunately I thought I can reconstruct the arguments, but some detail I am not able to recollect. I will look it up and I will explain it in the next class. But eventually from here we get the charge current potential to be root 2 GF times the number density of the electrons. Yeah.
There we are trying to calculate the amplitude of the
scattering. Yeah.
How is the amplitude and the potential related?
I mean, that is the detail I am not able to explain properly. I will look it up and I will explain it in the next class. But for the moment, let us assume that the interaction of neutrino passing through matter is given by this potential. Of course, there is a potential term coming due to charge current scattering. There is a potential term coming due to neutral current scattering. For the moment, we won't make a distinction between the two. We will say that there is a potential, and later I will show you that the neutral current scattering term doesn't matter, only the charge current term matters. By the way, this I have said, from this one I get a potential of this form, and for neutral current scattering I can derive a similar looking formula. Again, I do not remember the exact detail. I will look it up and I will explain it in the next class, how this potential, what is the exact form of this potential. Now, so there is a potential V, which in general is VCC plus VNC. And energy is P square plus M square plus the potential. And from here we find that E square, I bring this V to this side, minus 2EV plus V square is equal to P square plus M square. And here I make an approximation. The approximation I make is that V is quite small, so that in this expansion 2EV is much larger than V square. So I drop the V square term. This is justifiable because V after all is proportional to GF, and GF is the weak coupling constant and it's quite small. So I rewrite this equation as E square is equal to P square plus M square plus 2EV. I have deliberately put parentheses here because if you remember in our discussion about oscillations, vacuum oscillations, p square is much larger than m square, and it's the small difference between m1 and m2 which, when we take into account, we get oscillations. If we ignore that difference, there are no oscillations. So I'm now saying that this V, which is also small, it is also going to cause differences, and I'm going to combine it with m square, and it is the net effect of m square and 2ev which is going to cause oscillations. And having written like this, I make exactly the same approximations I made before. The ultra-relativistic approximation, equal momentum approximation, etc., etc. And by doing that, I get E is equal to P plus m square plus 2ev by 2p, which is approximately p plus m square by 2ev plus v. Is it fine so far? Yeah. Huh? What? From here to here? Huh? No. Are you okay with this? Yeah. And here I have taken square root and used the binomial expansion, just like I did in the case of vacuum oscillations. And now you see one tricky issue. I happily wrote down this formula, but I have not said whether I'm writing this formula, in which basis I'm writing this formula. Am I writing it in the flavor basis or in the mass basis? And the tricky issue is m squared is well specified in the mass basis, but the potential V is well specified in the flavor basis. So, in writing this formula, I actually cheated, because I should first specify what basis I am talking about, and then in that basis I should write what m square is and what V should be. Instead of which, I sort of happily wrote it like this and did these manipulations. But manipulations, the ultra-relativistic approximation still holds, independent of the basis. And this formula also holds. So all I have to do now is to be more careful and write things in appropriate basis. So I will choose to write my neutrino evolution equation, in flavor basis. So I write I ddt nu e and nu mu is equal to, or let me actually write it in a different way. That is actually more illustrative, more illuminating. Yeah. First, let me write for no matter effect. Not in flavor basis, but in mass eigen basis. I assume there are no matter effects to start with, and I write my evolution equation. And this is root p square plus m1 square 0 0 root p square plus m2 square. You agree to this? So simple Schrodinger equation. And so nu1 of t is exponential minus I e1 t nu1 of 0 dot dot. And if I make the ultra relativistic approximation, this is p times identity plus m1 square by 2p 0 0 m2 square by 2p times mu1 mu2. And again, let me emphasize, it is the inequality of M1 and M2 which is giving rise to oscillations. And I will write this as by the way, I replace the P in the denominator by E, which we have been doing, times identity plus 1 over 4e minus delta m square 0 0 delta m square mu1 mu2. So I have taken out a term m1 square plus m2 square by 4e common out. So that leaves this to be minus delta m square by 4e and this to be plus delta m square by 4e. And now comes a key point in introducing matter effects. We saw that matter effects come as a potential in addition to this term, but that potential is diagonal in the flavor basis. So what I should do is to transform this evolution equation from mass eigenbasis to flavor eigenbasis. Usually the mixing we introduce as nu e nu mu is equal to O times nu 1 nu 2, but here we are writing it in ulta. So if I substitute it here, this cos theta, sin theta, they are all constants. So this ddt in principle acts on both O transpose as well as nu e nu mu. But since these are constants, I can pull it out through the derivative, and ddt acts only on nu e nu mu. And having pulled out the O transpose, I take it to the right hand side as O. So I get the equation I ddt of nu e nu mu is equal to O times P plus m1 square plus m2 square by 4t times I plus 1 over 4t times minus delta m square 0 0 delta m square times O transpose times mu. So this is how the vacuum time evolution equation looks in the flavor basis. Now you see that this first matrix is proportional to identity, and there is a O on the left hand side, O transpose on the right hand side. But O times identity times O transpose is identity again. So making this transformation from the mass basis to flavor basis leaves this identity completely untouched. The change occurs only here. And this is a traceless matrix, and the similarity transformation leaves trace unchanged. So I should get a traceless matrix, which also turns out to be a symmetric matrix because I've taken a diagonal matrix and made an orthogonal transformation on it, and I get a symmetric matrix in that case. So this is the explicit form of the evolution equation in flavor basis for the case where there are no matter effects. And now I have it in flavor basis. Adding the matter potentials is straightforward. There is a term which connects nu E to nu E, which I call V nu E, and there is a term which connects nu mu to nu mu. So you look at what does the 1-1 term here do? 1-1 term is the part of the evolution of nu E which is proportional to nu E. That is what the 1-1 term is. Whereas the 1-2 term is part of evolution of nu E that is proportional to nu mu. And if you look at the expression for nu E, if you look at the expression for this potential for nu E, initial state is nu E, final state is nu E. So which means nu E is remaining nu E. So these matter potentials, they appear as diagonal matrix elements in this equation. Now so I have I ddt nu E nu mu is equal to plus 1/4e times this matrix plus VCC nu E plus VNC nu E 0 0 VNC nu mu times nu E. In the case of electron, I put two terms, the charge current potential and the neutral current potential. Whereas in the case of muon, I put only the neutral current potential. And if you remember, the electroweak theory guarantees that the neutral current potential for nu E is exactly same as the neutral current potential for nu mu. So that's proportional to an identity matrix. So I transfer it here. And this VCC also, I will split it into two. I write VCC by 2 times identity plus VCC by 2 here and minus VCC by 2 here, so that the sum is VCC here, 0 here. So if I do that, I get because the matter consists of electrons. If I need to have a charge current term for muon, I must have muons in my matter, and I don't.
How is it that, I mean, the electrons are in the matter? Let's say Earth, it's not really uniform distribution. I mean,
Yeah,
how
but
are we extracting a potential out of?
no, but there are electrons. I mean, for example, how if you look at the derivation of the refractive index, photons are going through neutral matter, but the refractive index is assumed to arise through the interaction of the photons with the electrons in the neutral matter. The same thing here. Times identity plus 1 over 4e times minus delta m square cos 2 theta plus a. I should rewrite this in a slightly better way. There, this A is 4e times VCC mu e by 2, that is 2EB. I said that VCC I am splitting into 2, VCC by 2, but I have pulled out a 1 over 4e, so I have to multiply by 4e. So I get this, and this is defined. It is given a formal name A, and this is called Wolfenstein term or Wolfenstein Matter term, because Wolfenstein is the person who first did this analysis. So now this is a traceless symmetric matrix, and if I make an orthogonal transformation on it, I will get a traceless matrix with eigenvalues minus delta m square prime plus delta m square prime. But if I make the same orthogonal transformation on this, identity remains identity. And all these terms which are proportional to identity do not have any effect on oscillations. Anything that affects nu e and nu mu the same way does not lead to any oscillation between nu e and nu mu. It is the difference between nu e and nu mu properties that leads to oscillations. So that is why you see that the potential coming from neutral current terms does not affect oscillations between active flavors. But suppose I am considering oscillation between nu e and nu sterile, then nu sterile does not have this. So there the neutral current term also will play a role in oscillations. So that matrix in ordinary brackets, it's a traceless symmetric matrix, and by making an orthogonal transformation I can diagonalize it. So I choose nu e nu mu to be OM times nu1m nu2m. This is cos theta m sin theta m minus sin theta m cos theta m times so I assume that there are two matter dependent mass eigenstates nu1m and nu2m. And if I rewrite this equation in that basis, then this matrix will be a diagonal matrix. And the nu1m basis, nu2m basis is related to the flavor basis through this orthogonal transformation. It looks just like the vacuum transformation, except that I'm calling my mixing angle theta m. That is, it is modified by matter effects. And if I substitute here, if I substitute this here, again the ddt is acting both on OM as well as on nu1m and nu2m, which means that the ddt is acting on theta m. Now, what does theta m depend on? Theta m depends on the original mixing angle, the mass square difference, but they are constants. In addition, theta m depends also on this Wolfenstein term A. Now, is this Wolfenstein term constant or not constant? If you remember, we wrote this VCC being proportional to the electron density. Now, as the neutrino is moving through matter, does it see a constant electron density or does it see a varying electron density? That's the issue. If it sees constant electron density, which is the case when the neutrino is moving through the crust of the earth, then we treat this a to be constant, then theta m is also a constant, and we can pull it out of the derivative. But if for a neutrino traveling through the sun, the density of the sun changes quite rapidly, so one has to worry about the changing density of the sun and the corresponding change in theta m because of that. So for the moment, I will not make any assumption. So I'll just substitute it there, and we write the algebraic expressions, and then we will consider different limits. So I have I ddt of OM nu1m nu2m is equal to, by the way, to keep it, to stop me to repeat things and unnecessary things, I will now drop things related to identity. So I will write only the terms that will make a difference. 1/4e times minus delta m square cos 2 theta plus a delta m square sin 2 theta delta m square sin 2 theta delta m square cos 2 theta minus a times OM nu1m nu2m. Now on the left hand side, I have dOm dt acting on nu1m nu2m plus OM acting on I ddt nu1m nu2m.
So what is the physical difference between these mass eigenstate and
We'll come to it. We have to first do the algebra, finish the algebra, and sort of try to extract what that algebra is telling us. And I multiply throughout by OM transpose. So if I do that, I have OM transpose here, and this drops out, and this term, this will acquire a OM transpose here on the left hand side. And then in order to make it look like a standard Schrodinger equation, I take this term to the right hand side. If I do that, I get I ddt times nu1m nu2m is equal to, I get two terms now, 1/4e times OM transpose times that matrix OM, not plus, I'm taking it on this side, so it will be minus I OM transpose BOM BP mu 1m. Now, I make my first approximation. We assume that is the number density of electrons doesn't change with time, so the Wolfenstein matter term does not change with time. So this term does not bother us, and we choose theta m such that OM transpose times OM is minus delta m square m 0 0 delta m square m. We choose the orthogonal matrix in such a way that the symmetric matrix becomes diagonal, and since the original matrix is traceless, the corresponding diagonal matrix will also be traceless. So basically you multiply these three matrices, you get some complicated looking expression, and you set the off diagonal element to be 0, and you get the condition that implies tan 2 theta m is equal to delta m square sine 2 theta divided by delta m square cos 2 theta minus a. And you will also get delta m square m is equal to delta m square cos 2 theta minus a whole square plus delta m square sine 2 theta whole square under root. And note that if I put a equal to 0, I get back the vacuum value both here as well as here. By the way, this equation is better written well. And notice something interesting. And this is why that, by the way, up to here I think Wolfenstein did and sort of left it, so to speak. But 5 years later, Mikhail and Smirnov, they said, imagine a situation where the value of delta m square and value of theta are fine-tuned such that they are equal to A. Then the denominator vanishes, which means tan 2 theta matter diverges. That means 2 theta, rather tan 2 theta matter divergence means 2 theta matter is pi by 2, which means theta matter is pi by 4. And pi by 4, if you remember from the vacuum, is what we call maximal mixing. That is when sin 2 theta m takes the maximal value. So, even if your original mixing angle theta is very small, dynamically you are able to enhance the mixing from a small mixing angle to a large mixing angle. But of course, you need a fine-tuned solution. We need delta m square cos 2 theta of the order of A. Only then this amplification occurs. However, we have to be careful. Remember, we are talking about constant matter density. So, once for a given energy, theta m is fixed. And of course, a neutrino has a given energy. So, if that neutrino is passing through constant matter density, then A for that neutrino is fixed, which means theta m is fixed and delta m square m also is fixed. And so the situation now is very similar to the vacuum mixing case. I have the flavor eigenstates nu e and nu mu. Now the propagation eigenstates, they are not nu1 and nu2. Instead, they are nu1m and nu2m. But they are related to nu e and nu mu through this orthogonal matrix, where the orthogonal matrix is parameterized by a constant angle theta m. So, calculation of oscillation probabilities is just like in the case of calculation of oscillation probabilities for two flavor vacuum mixing. So, we have P nu e to nu e is 1 minus sine square 2 theta m sine square 1.27 delta m square m L over T. I just replace mixing angle by matter dependent mixing angle and the mass square difference by matter dependent mass square difference. And similarly for nu mu to nu e, etc., etc. Now you say, I will fine tune my energy so that delta m square cos 2 theta equal to a. So this becomes 1. But if you look at this expression, this is becoming 0 and delta m square m now is, my claim is I am boosting the mixing angle from a small angle to sine square 2 theta equal to 1, which means, but when I do that boosting, my delta m square is taking a minimal value. So the energy at which the mixing angle is taking the maximum possible value, my mass square difference is taking a minimum value. So if L is fixed, I'm not really gaining anything. I'm boosting this, but I'm losing here. So in order to take advantage of this, I should have variable L, so that if this is becoming minimum, I should be able to increase this L so that I still get 1 from here. And that we are able to do only in atmospheric neutrinos, where I have a variable L. These issues, it turns out, they don't matter in the case of the solar neutrinos. The reason is, the solar neutrinos are passing through matter of varying density. So this approximation I made, this is not correct. However, I make another approximation which you have heard of in quantum mechanics, that is called adiabatic approximation. I assume that things are changing, but I'll also assume that they are changing slowly. And under the adiabatic approximation, I will derive the expression for an electron neutrino emitted at the center of the sun to emerge from sun as an electron neutrino. And I find that that probability is independent of L. It depends only on the mixing angle. In fact, it depends on the matter modified mixing angle. Therefore, if I am able to get a amplification of the mixing angle, that is good enough as far as the solar neutrino problem is concerned. And if you remember, originally in the case of solar neutrinos, they have observed a suppression factor of 1/3. And within two flavor oscillations, it was impossible to, within two flavor vacuum oscillations, it was impossible to get suppression fraction of 1/3. And what Mikhail-Smirnov showed in 1985 is that in two flavor oscillations, it is possible to get a suppression fraction of 1/3, but through such a mechanism, even if original theta is very small, even if it is some 3 or 4 degrees. But later data from solar neutrino experiments showed that actually the theta for relevant for solar neutrino data is something like 35 degrees. But still, this matter modifications proposed by Mikhail and Smirnov are still relevant in the case of solar neutrinos, and I will discuss that in next Wednesday's class. So we will discuss the case of slowly changing dA dt, and we will derive the solar neutrino oscillation probability in Wednesday's class. And also I will clarify how from that scattering matrix element, how we get the charge current potential, and from the how we get the neutral current potential. That also I will clarify in the next class.